Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will talk about the CDF of the exponential distribution. Well, to be more specific, what we're going to be doing is this. First, we are going to derive the CDF of an exponential distribution, and then we are going to use it to solve a problem from your textbook. Okay, so that's the plan. First things first, let's try and derive the expression for the CDF of an exponential distribution, or for a random variable y with an exponential distribution. Okay, so first, this is just notation. What we have here is if y is a random variable with an exponential distribution and parameter beta, right? Just remember that we statisticians are lazy writers. So instead of writing y as, well, y is a random variable, y is distributed as an exponential with parameter beta, you'll see this kind of expression in some textbooks, including our own. Okay, so if that's the case, then we use that capital F. Remember, that's just notation for the CDF, meaning the cumulative distribution function, right? So we know that our PDF will be non-zero, right? It's going to be above the horizontal axis when you have a positive, or I should be more specific, a non-negative real number. Okay, so in that case the CDF will be given by 1 minus e to the negative k divided by beta. I'm just using a different letter here, so we are evaluating at a number k that is non-negative, a non-negative real number. And in the case that you have a negative number, well, the CDF will be 0. Okay, let's try and show that. Okay, so first, let me copy paste this guy. Uppercase f of y evaluated at k, that is just the probability that the random variable y is less than or equal to k, right? Okay, now in this particular case, since we are dealing with a continuous random variable that happens to be the integral from negative infinity to k of the corresponding PDF, probability density function, with respect to y. Okay, now we are going to break down that integral into two. First, from negative infinity to 0, but in that case the PDF of an exponential is just going to be 0 plus, then we have the integral from 0 up to k of the PDF. In this case, we have an exponential distribution with parameter beta, and we use this expression 1 over beta e to the negative y divided by beta. Okay, so that's the expression that we're using in our textbook. Okay, great. The first integral, easy, right? It's just a 0. So this one is the interesting one. Let me copy paste that guy. There we are. Now, we have seen that before, right? And it's easy to integrate we know that if we had a negative 1 over beta here, that would be easy. Very easy to integrate, because it would be the integral of negative 1 over beta times e to the negative y divided by beta. The y would be just e to the negative y divided by beta. So since we need that negative sign, let's multiply by a1, and then that's a legitimate way of getting it. Okay, so now we know what the integral is going to be. Let me place that negative 1 outside. Now what I want is just I just want to evaluate that guy, right? E to the negative y divided by beta. I want to evaluate it at 0 and at k, right? Okay, so no problem. So we have a negative 1 there multiplying outside, and then we have e to the negative k divided by beta, right? So e to the negative y divided by beta. Oh, negative k, because we're evaluating at k, right? Okay. And then e to the negative 0 divided by beta, e to the 0 power, that's just a beautiful 1. So then we just multiply by negative 1, and what we have is, in the end, 1 minus e to the negative k divided by beta. Agreed? Okay. Let me just copy paste that guy, and that's the CDF evaluated at k. Guys agree? Now note that if k, right, in the case, what we did here was the case when k is greater or equal to 0, right? If k was less than 0, the only part that you would have would be this, the first integral. So if k was negative, then it would be just this integral, and that clearly is 0. So we are done. We have shown that if k is positive or 0, it's going to be this expression. If k is negative, then the CDF will be 0. Okay, so next step, we would like to apply that result to this exercise, exercise 4.89. I think we have it here in our lecture notes, so that's the one we want to do. Let's try and solve exercise 4.89. So we have an exponential distribution as expected. We are given that information, that the probability that the random variable is greater than 0.08, we have that the probability that the random variable is greater than 2 is 0.08 to 1, right? Okay. So now, the parts that we would like to answer are parts A and B. We would like to find the parameter of that exponential, beta, okay? And we know, we have shown already together that, well, beta happens to be also the expected value of an exponential distribution, okay? Okay, so if we find beta, we find for free its expected value. Okay, and the second part is finding a particular probability, the probability that y is less than or equal to 1.7. Well, first, let's take that piece of information, the probability that y is greater than 2. We're given it's 0.08 to 1. Okay, so solution. We might as well open a new one. So solution for that exercise. As I said, we are given that the probability that that random variable y is greater than 2 is just 0.08 to 1, right? Okay. Now, take a closer look at the left-hand side of that equation. As you can imagine, we would like to use our CDF, right? We have already spent some time getting it. Well, we want to use it. So we would like to rewrite that in terms of something we can use. Well, something we can use is this. That probability, the probability that y is greater than 2, is equivalent to 1 minus the probability that y is less than or equal to 2. But we know that that probability, right, is just the CDF of y evaluated at 2. So let's write it down like that. Okay, so that would be uppercase F, meaning the CDF of the random variable y evaluated at 2. And there you go. Oh, we have, a very general expression for that CDF, right? We have that right here. Uppercase F, meaning the CDF of the random variable y evaluated at k when k is positive or 0 is 1 minus e to the negative k divided by beta. So in this particular case, our k happens to be 2. So let me copy paste this guy here, and let's go back to this one. So we have 1 minus f evaluated at 2. I'll change that one in a sec. So k is 2 in this case, equals 0.08 to 1. Nice. So we have 1 minus 1, 0, minus times minus, that's a plus. So we have e to the negative 2 divided by beta equals 0.08 to 1, right? Okay. So if we go back to the problem, we want to find beta. So what we have to do is just solve for beta from that last expression that we had, right? So let's just apply natural log on both sides, and what we end up with is, 2 divided by beta, maybe I should say negative 2 divided by beta equals natural log of this guy, 0.08 to 1. Okay, so now what we want is just solve for beta. So we could multiply by beta on both sides and then divide by natural log of 0.08 to 1, and then we're done, right? So let me do that. Let me copy paste this and then rearrange the terms. Let me move this guy around here. And now I want beta on the right hand side of my equation. We're done, right? Okay. So now we want to find that natural log of 0.08 to 1. Okay, so let me use R. So natural log of 0.0821. Oh, no natural log. Guess what? So log of 0.0821. And I wanted you to see this. Can you see this here? Right? So the base is by default exp at the power of 1. So the base is e. Okay? So, and this is something that you'll see in a bunch of statistics textbooks, right? When we statisticians write down log, we don't mean log base 10. We mean natural log, ln. So in a statistics textbook, make sure that you check that. If you see log, make sure that it's not natural log. Usually that's the case in statistics textbooks. When you see log, just plain log, what we mean is ln. So let's see. Okay, so we have this, right? But what we want is minus, well, 2 divided by that times minus 1. Okay, so let's do minus 2 times, well, minus 2 divided by this guy here. Okay, so roughly 0.8. Okay, beta is roughly 0.8. Okay, 4 decimal places, 0.8. Okay, so now let's do part B, because we're done with part A. We have found beta, and we have just for free the expected value as well. That's going to be the expected value. Okay, part B. So remember that we wanted a specific probability. We wanted the probability that the random variable is less than or equal to 1.7. Okay? Okay. Okay, so probability that the random variable is less than or equal to 1.7, right? Okay, but when you see that, immediately you go, hey Al, that's just uppercase F, meaning the CDF, evaluated at 1.7. And we already have that. We derived general expression for an exponential with parameter beta, any beta. And now we have beta. So let's use it. It's this guy, right? This case, we're not going to be evaluating at 2. We are evaluating at 1.7. So it's that guy at 1.7. And we had from part A that beta is 0.8. So just have to do the math and we'll have that probability. Okay, here we go. So it would be just exp negative 1.7 divided by 0.8. But that's not exactly what we want. We want 1 minus that, right? Okay. So that is just roughly 88.05%. Okay. So that's a probability. Well, let's summarize what we did here in this video. First, we obtained a general expression for the CDF of an exponential distribution. Then what we did is we used it to solve this exercise. And in this case, for this exercise, beta was unknown. So having the expression in general of the CDF was very helpful, especially given the piece of information that we had here, because that probability could be re-expressed in terms of the CDF, right? The cumulative distribution function. So that's what we did to find beta. Something else that we learned along the way, in case you didn't know that, is that in statistics, when you see log, usually what we mean is natural log, not log base 10. Okay, so just keep that in mind when you see statistics textbooks. And then to solve the second part was a direct application of the formula we already had for the CDF of a random variable with an exponential distribution. Well, that's it. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.